So we have a set of examples where we are trying to find the critical numbers of a function. Recall are points where the derivative of the function is equal to 0. Now, oftentimes we do this mathematically and we can verify our answer using a calculator. You would see the relationship between the critical numbers and the extrema when we go to finding the extrema of a function. So the very first step is to find the derivative. F prime of x is 2x minus 1 over 2. Derivative of 1/4 is 0. You set the derivative equal to 0 and you solve for x. So 2x minus 1 over 2 is equal to 0. This would imply 2x is equal to 1 over 2. So x would equal to 1 over 4. So the critical number or value is x is equal to 1 over 4. Same process, only this time we have a cubic polynomial. So when we have a cubic polynomial, the process is pretty much the same, but when we take the derivative, we are going to have a quadratic equation. So the first step is to find f prime of x. So f prime of x is 3x squared plus 8x minus 15. Step 2, set f prime of x equal to 0 and solve for x. So we have 3x squared plus 8x minus 15 equals 0, and that is a quadratic equation. And how do we solve a quadratic equation? We make use of the quadratic formula. The formula is minus b plus or minus square root. So a here is 3, b is 8, and c is minus 15. So minus b plus or minus b squared minus 4 times a times c divided by 2 times a. So we have minus 8 plus or minus square root of 64 plus 180 divided by 6. So minus 8 plus or minus square root of 244 divided by 6. 244, if I pull a 4 out, is 61. So we have minus 8 plus or minus square root of 61 times 4 divided by 6. And if we pull the 4 out, we have minus 8 plus or minus 2 root 61 over 6. We can simplify and cancel the 2's. That would become 4, that would become 3. So the two values are minus 4 plus square root of 61 over 3 and minus 4 minus square root of 61 over 3. So those would be the critical values. So we have another example. Once again, we have a cubic polynomial, and the first step is to find the derivative. F prime of x is 6x squared plus 8x plus 4. The second step is to set f prime of x equal to 0 and solve for x. So 6x squared plus 8x plus 4 equals 0. And we have a 2 in common, so we can divide by 2 on both sides. So 3x squared plus 4x plus 2 equals 0. Once again, that is a quadratic equation, and if we can solve it using factoring, it's great. If not, we have to use the quadratic formula. Looks like we have to use the quadratic formula in this case. So A is 3, B is 4, and C is 2. And the formula is minus B plus or minus square root of b squared minus 4ac divided by 2a minus 4 plus or minus square root of 16 minus 4 times 3 times 2 divided by 2 times 3. So minus 4 plus or minus square root of 16 minus 24 is minus 8 divided by 6. If I pull the root out, I have minus 4 plus or minus, I'm going to pull a 4 out of the root. It is going to become 2, and I'll have minus 2 divided by 6. I have a 2 in common, so I'm going to cancel that out. I end up getting that. So this is interesting. So you look at these values and you say, oh, well, we have imaginary numbers here, so, well, perhaps they are the critical values. If you get imaginary numbers, then you don't have critical values. Of course, we have complex critical values, but we want real numbered values for the critical values. So this particular function doesn't have now, because we want real numbered values. Now, what is the consequence of having imaginary critical values? I'm going to plug in the original function, which is 2x cubed plus 4x squared plus 4x. I'm going to graph this, and I end up getting that. Now, by zooming in, maybe I would set the window between -2 and +2. And you can see this particular curve doesn't have a well-defined maximum or minimum. It just kind of doesn't have a proper peak, even if you zoom further in. And you can see that there is not a well-defined absolute maximum, minimum, or local maximum or minimum, which is why we are getting imaginary critical values. So in this particular case, the function doesn't have any critical values that are real. Okay, now we move on to the next case. So here we have f of x is equal to the absolute value of 3x plus 2. Now this is an absolute value function, so we need to have a piecewise component here. Now, what do we know about an absolute value function? When it comes to absolute value functions, graphing is a great tool. So I'm going to graph this. So when I graph, get a picture of that sort. I'm going to zoom in -5 to 5, and we have that. Even though the function is continuous, that tip of v will be at -2/3. So that point right there is -2/3. And even though the function is continuous, there is a sharp turn. So there is at x is equal to -2/3. This would imply that the derivative doesn't exist at x is equal to -2/3. Keep in mind, if the derivative doesn't exist, then we could have a critical value at that point. So x is equal to -2/3 is a critical value. So for us to call a number as a critical number or a critical value, the derivative either must equal to 0 at that point, or it must not exist at that point. So this is a case where the derivative doesn't exist and we end up getting a critical value. So now we have trigonometric functions and we want to find the critical values. So the first step is to find the derivative. So derivative of sine t is cosine t. Derivative of cosine raised 4t is 4 cosine cube t. Multiplied by the derivative of cosine t, we have negative sine t. So that would give us 4. I have a cosine t in common. If I pull that out, I'd have 1 minus cosine squared t times sine t. So we want to set f prime of t equals 0 and solve for t. I don't want to overcomplicate the problem, so I am going to say t has to be between 0 less than t or less than or equal to t less than or equal to 2 pi. The reason why I'm confining it to an interval is because I want to ignore the periodicity because sines and cosines have a periodic behavior, and it'll keep on going, and you'll have plenty of maxima and minima and critical numbers. So I'm just going to look at the interval between 0 and 2 pi, including the endpoints. So we have to solve for t by setting the derivative equal to 0. So 4 cosine t multiplied by 1 minus cosine squared t sine t must equal 0, which would imply 4 cosine t equals 0. That would be the first part. Or the second part, 1 minus cosine squared t times sine t would equal 0. Now, I could rewrite this as 1 equals cosine squared t times sine t. Now, for what value of t would a cosine be equal to 0? We know when t is pi over 2, a cosine is 0. When t is 3 pi over 2, cosine is 0. You can plug it in a calculator and you can find that easily. Now that was pretty straightforward, but the other one here though, it's kind of is tricky, because we have 1 equals cosine squared t times sine t, and when I multiply the two I must end up getting 1. So how would we go about doing this? For that particular case, I recommend using the calculator, even though we could find it using trigonometry. I recommend that you guys use a calculator because it would be easier. So what we are trying to do is we are trying to find the zeros of this function. We are trying to find where 1 minus cosine squared t sine t equals 0. So I'm going to plug in that expression, 1 minus cosine squared which is simply cosine t squared multiplied by sine t. I'm using x instead of t, and I would like to find where this becomes 0. And you can see, you should see something now. I don't know if you're seeing that. Let's set it to 0 to 2 pi. Now what do we see? The curve keeps on going, but does it ever cross 0? It doesn't seem like. There is no point where this particular condition would be satisfied. As I said, if you use a bit of trigonometry, you will find out that this is not going to happen for any value of t. So there is no value of t satisfying the above equation. So the only critical values that we are left with are t equals pi over 2 and 3 pi over 2. So if we were able to find values of t that would satisfy the second equation here, then we would have more critical values, but unfortunately in this problem there is no other value that would satisfy that particular equation, so we don't have any more critical values. Here is another function that has exponentials and a regular quadratic function. So the very first step is to find the derivative. So here we have u and v, it's a product of two functions. So we have to use product rule. du is 2x, dv is negative 4 e raised negative 4x, or simply u prime. I think it should be easier to call it u prime v prime. 2x, v prime is minus 4 e raised minus 4x. So the derivative is u v prime plus v u prime. U is x squared, v prime negative 4 e raised negative 4x. V is e raised negative 4x. U prime is 2x. And we can say e raised negative 4x is common, so we could pull that out. And we have x squared times minus 4, which is minus 4x squared, plus 2x. And that would be the derivative. And we also say that we have a 2x in common. So 2x, if I pull that out, I have e raised negative 4x multiplied by negative 2x plus 1. Great. Now we have to set the first derivative equal to 0 and solve for x. So 2x e raised negative 4x multiplied by negative 2x plus 1 equals 0. Now I have three different parts here. That function, and that function. So those are all factors of the first derivative. So I'm going to set 2x is equal to 0, e raised negative 4x equal to 0, negative 2x plus 1 equal to 0. If 2x is equal to 0, we end up getting x to be equal to 0. Now, this could never be true. So there is no value of x that would satisfy the above equation. Why? An exponential becomes 0 only in limit. So we don't have a solution there. Over here, 2x would equal to 1, which would imply x is 1 over 2. So the critical values are x is equal to 0 and x is equal to 1 over 2. We could have found this using a calculator, so I'm going to show you how. Let's plug in 2x e raised negative 4x multiplied by 2x plus 1 and graph. I see something here. Window, let's reduce to negative 1 to 1 graph. Okay, so it seems like it's crossing at 0 and it's crossing at negative half. Did I miss a negative here? U, v prime, v, u prime. Let me zoom this a bit. So I got the 1 at 0, but there is another 0 crossing, so let's just go ahead and... So this is why a calculator is very useful. So let's do second trace. We want to find a 0. I'm going to go to the left here and to the right and guess. Negative 0.5. Looks like I have missed a negative sign somewhere. U v prime plus v u prime have an x squared, and I pull a 2x out. That is strange. Give me 1 second here. Something is amiss. And it just can't be. Did I type something wrong here? It's 2x. Aha! That should be negative. Second insert. Negative 2x plus 1. Okay. So now our world is perfect. So we can zoom this further and narrow it down to, say, -1 to 1. Guess we have to zoom further more. We'll do -0.5 to 0.5. And now you can see that there is a 0 crossing at 0.5. So our critical values are x is equal to 0 and x is equal to 0.5. So I could find those zeros by doing second trace and to the left of the first 0 and go to the right. Enter. I get 0 as the first 0, and I repeat the same process. Second trace, number 2, go to the left of the next 0, which is right over there close to the cursor. Enter. Move, cross the 0 and over to the other side. Enter, enter, and I get 0.5. So the two critical values are x is equal to 0 and x is equal to 1/2. So here is, this should be a function of x, not t. We want to find the critical numbers for square root of 4 plus x squared. So the first step is to find the derivative. So f prime of x, that is simply 4 plus x squared raised 1/2. So we would have 1/2, 4 plus x squared, raised 1/2 minus 1, multiplied by the derivative of the inside, which is 2x. I am using chain rule here. And that would equal to 1/2, 4 plus x squared raised -1/2, multiplied by 2x. The 2's would go away. We have x multiplied by 4 plus x squared raised -1/2, which is x over 4 plus x squared raised 1/2, and that would be x over square root of 4 plus x squared. Now we have to set f prime of x equal to 0 and solve for x. So we have x over square root of 4 plus x squared is equal to 0. Cross multiply by square root of 4 plus x squared on both sides. Those two would go away, which would mean x is equal to 0 is the only value that would satisfy the equation. You could actually find this using the calculator as well. So I have x divided by square root of 4 plus x squared. And you can see it crosses the x-axis at x is equal to 0. So the critical value is x equals 0. You can either call it a critical value or a critical number, it's entirely up to you. So here is another one that involves logarithms. So again, we have to use product rule, or we could do quotient rule. So let's try to rewrite this. We could rewrite x raised negative 1 as 1 over x multiplied by ln of x squared. We have to try our best to simplify it as much as possible prior to finding the derivative. Is there a way to simplify? If I use the properties of logarithms, I could actually move the 2 inside the logarithm out to the front, and I could have 2 over x multiplied by ln of x. So now I could find the derivative. U would be 2 over x and v is ln of x. U prime is negative 2 over x squared and v prime is 1 over x. So f prime of x would be u v prime plus v u prime. So 2 over x multiplied by v prime, which is 1 over x, plus v ln of x multiplied by u prime, negative 2 over x squared. So we have 2 over x squared minus 2 over x squared multiplied by ln of x. And we have 2 over x squared in common, and that is our derivative. So set f prime of x equal to 0 and solve for x. So we have 2 over x squared, that is the first factor, multiplied by 1 minus ln of x equal to 0. Obviously the first factor would never become 0, so we have to set that equal to 0. 1 minus ln of x equals 0, which would imply ln of x is equal to 1, which would imply x is equal to e raised 1. I'm raising to the power of e on both sides, so e raised ln of x is equal to e raised 1. Those two go away, and I end up getting x to be equal to e. So the critical value and that is 2.71828. So the purpose of finding critical numbers is to determine the maximum and minimum values of a function. So we could find the local minimum, maximum, we could find the absolute minimum and maximum just by finding the critical values. So in order to find the absolute maximum, absolute minimum, so what we're going to do is we have an interval which is 0 to 5. So the domain of f of x is 0 to 5, and f of x is 12 plus 4x minus x squared. Now, first step is to find the derivative. So we have 4 minus 2x. Second step, set f prime of x equal to 0 and solve for x. So this would imply 4 minus 2x equals 0. So we have 4 equals 2x. X would equal to 4 over 2, which would imply x is 2. X is 2, and 2 lies in between 0 and 5. So we have a critical value in the domain of the function. So that is the critical number. So since that is a critical number, there has to be a minimum or a maximum at that point. Now, how do we determine if we have a minimum or a maximum? We could use the extreme value theorem. Let's find f of 0. F of 0 is 12 plus 4 times 0 minus 0 squared, which is 12. F of 5 is 12 plus 4 times 5 minus 5 squared, which is 32 minus 25, you get 7. And f of 2 is 12 plus 4 times 2 minus 2 squared, which is 16. So here I have zero, 2, and 5. And at 0, I had a value of 12. Let's just say that's 12. And at 2, I went up to 16. And at 5, I went down to 7. So clearly, I have a peak at 2, and that has to be an absolute maximum. Now, what is the absolute minimum? The absolute minimum occurs at x is equal to 5. Right there. So the absolute minimum is at the point 5, 7. The absolute maximum is at 0, 12. You can make use of the calculator to verify this also. I'll show you how. So let's go ahead and enter the function, which is 12 plus 4x minus x squared. And the domain is 0 to 5. And I'm just going to graph. Perhaps we have to go from 0 to 20. And you can see that's pretty much the curve that I have, and at 2 we end up having a maximum. Okay. So graphing is very useful when it comes to a problem dealing with maximums and minimums. So here we have a cubic polynomial and the interval is -2 to 3. So the very first step is to find the derivative. And that would be 6x squared minus 6x plus 12, because the derivative of 1 is 0. The domain is -2 to 3. We're going to set f prime of x equal to 0, and we will solve for the critical numbers. So f prime of x, we know it already, that is 6x squared minus 6x plus 12 equals 0. We have a 6 in common. 6 times x squared minus x plus 2 equals 0. Divide by 6 on both sides. We would get x squared minus x plus 2 equals 0. That is a quadratic equation. So x is minus b, so minus of -1, plus or minus square root of b squared, which is 1, minus 4 times a times c, divided by 2 times a. So we have 1 plus or minus square root of 1 minus 8 divided by 2. 1 plus or minus square root of -7 divided by 2. 1 plus or minus I root 7 divided by 2. And clearly, this is not real. So what we're about to say here is this particular function doesn't have any absolute maximums or minimums in the middle between -2 and 3. So all we can say now is find f of -2, which should be 2 times -2 cubed minus 3 times -2 squared plus 12 times -2 plus 1, -16, -12, -24 plus 1, which is -41. And f of +3, the other endpoint, is 2 times 3 cubed minus 3 times 3 squared plus 12 times 3 plus 1, 54 minus 27 plus 36 plus 1, and that is 64. So, if you graph this, you will see that this particular function doesn't have any peaks or dips. What do I mean by that? Let's go ahead and graph this. 2x cubed minus 3x squared minus 12x plus 1. And I'm just going to graph. Perhaps we should adjust the window here, -2 to 3, and have some really large values. So I'm just going to go from 0 to, or -60 to positive, -60 to positive 100. See what happens. That's what I end up getting. So looks like we've made a mistake somewhere. So let's go back and check out our equation. So this is why using a calculator is very useful. You can catch mistakes. Now I look at this picture and I can see a peak and a dip. But here I have no critical numbers, so I must have made something wrong. It looks like I ignored that negative sign. So that has to be a negative 12. So negative 12, negative 2, negative 2, which would change our roots. Minus b, plus or minus b squared, negative 1 squared, minus 4 times a times c, divided by 2 times a. 1 plus or minus square root of 1 plus 8 over 2. 1 plus or minus square root of 9 over 2. So we have 1 plus 3 over 2 and 1 minus 3 over 2. And we will have 4 over 2 and minus 2 over 2, which is 2 and negative 1. So we are about to have an extreme value at 2 and an extreme value at negative 1, which seems to be true by looking at the picture. If I trace, when I go closer to negative 1 over there, I have a maximum value, and I go down here to the right at x is equal to 2, I have a minimum value. Now that minimum value is about negative 18. So I have to make that change here also. Since my equation changed, I have to change f2 and f3. So f of minus 2 is 2 times minus 2 cubed, minus 3 times minus 2 squared, minus 12 times minus 2 plus 1. So minus 16 minus 12 plus 24 plus 1, which would give me minus 28 minus 4 plus 1 minus 3. And f of 3 would be 2 times 3 cubed minus 3 times 3 squared minus 12 times 3 plus 1. It's 54 minus 27 minus 36 plus 1, which is 27 minus 36, that's about minus 8. So what we have here, again using extreme value theorem, I have endpoints at minus 2 and 3. At minus 2, I have a value of minus 3. And at negative 1, I have a point up here. So the curve kind of goes like that. And at 2, I have a point right here, and it goes, actually lower than that, and it goes up there. So this point is the lowest, corresponding to x is equal to 2, the first critical number, so that would be the absolute minimum, and that point is the absolute maximum. And you can see that those two would correspond to the critical numbers negative 1, which is right here, and 2, so that's a critical number, that's a critical number, and those are the numbers that we found. So finding critical numbers would help us to find the absolute minima and maxima of a function.